Good morning, I'm A. Devasaina. In this lecture, we are going to discuss about root locus, that is, the stability analysis in time domain. This topic is present in the subject control system. Let us start discussing about the theory of the root locus. The root locus technique was introduced by W.R. Evans in 1948 for the analysis of control systems. The root locus technique is a powerful tool for adjusting the location of closed loop poles to achieve the desired system performance by varying one or more system parameters. Consider the open loop transfer function of the system. G of s is equal to k divided by s into s plus p1 into s plus p2. The closed loop transfer function of the system with unity feedback is given by C of s by R of s is equal to G of s divided by 1 plus G of s. We know the value of G of s as k divided by s into s plus p1 into s plus p2. Therefore, substitute this value in the closed loop transfer function. We obtain C of s by R of s is equal to G of s divided by 1 plus G of s, that is equal to k divided by s into s plus p1 into s plus p2 plus k. The denominator polynomial of C of s R of s is the characteristic equation of the system. The characteristic equation is given by s into s plus p1 into s plus p2 plus k is equal to 0. The roots of characteristic equation is a function of open loop gain k. When the gain is varied from 0 to infinity, the roots of characteristic equation will take different values. When k is equal to 0, the roots are given by the open loop poles. When k tends to infinity, the roots will take the value of open loop zeros. Let us see the representation of open loop poles and open loop zeros. The open loop poles are represented by a cross symbol and open loop zeros are represented by a small circle. This is indicated in this given S-plane. In the S-plane, in the x-axis we have real axis and in the y-axis we have imaginary axis. Let us see the definition of the root locus. The path taken by the roots of characteristic equation when the open loop gain k is varied from 0 to infinity are called root loci, or the path taken by roots of characteristic equation when open loop gain k is varied from 0 to infinity is called root locus. Let us discuss about the rules for the construction of root locus. Rule number 1. The root locus is symmetrical about the real axis. Rule number 2. Each branch of the root locus originates from an open loop pole corresponding to k is equal to 0 and terminates at either on a finite open loop pole or open loop 0 at infinity corresponding to k is equal to infinity. The number of branches of the root locus terminating on infinity is equal to p minus z, that is number of open loop poles minus the number of finite zeros. Let us discuss about the rule number 3, that is segment on real axis. Segments of the real axis having an odd number of real axis open loop poles plus zeros on their right are the part of the root locus. Rule number 4. The p minus z root locus branches that tend to infinity do so along straight line asymptotes making angles with the real axis is given by phi of a is equal to 180 degree into 2n plus 1 the whole divided by p minus z, where n is equal to 0, 1, 2, it goes on up to p minus z. That is, phi of a is equal to the angle of asymptotes. Let us discuss about rule number 5, that is determining centroid. The centroid is a point of intersection of the angle of asymptotes with the real axis is at s is equal to sigma suffix a. Sigma suffix a is equal to the sum of real parts of poles minus the sum of real parts of zeros divided by p minus z. Sigma suffix a is referred to as centroid. Centroid may be a part of a root locus or not. The centroid is a point where the angle of asymptotes intersects on the real axis. This may be a part of a root locus or may not be. Let us start discussing about determining breakaway or break-in point, rule number 6. The breakaway or break-in points of the root locus are determined from the roots of the equation dk by ds is equal to 0. If r number of branches of the root locus meet at a point, then the breakaway point at an angle of plus or minus 180 degree by r. The breakaway or break-in point must be the part of the root locus. This is the point where the root locus intersects on the real axis. Now we start discussing about the angle of departure and angle of arrival. Angle of departure is being calculated when we have complex poles in the given problem. Angle of arrival is calculated when we have complex zeros in the given problem. The angle of departure from a complex open loop pole is given by phi of p is equal to plus or minus 180 degree into 2n plus 1 plus phi, where n is equal to 0, 1, 2 and it goes on. And phi is the net angle contribution at the pole by all other open loop poles and zeros. Now we are going to determine the angle of arrival. The angle of arrival from a complex open loop 0 is given by phi of z is equal to plus or minus 180 degree into 2n plus 1 plus phi, where n is equal to 0, 1, 2 and it goes on. And phi is the net angle contribution at the 0 by all other open loop poles and zeros. The angle of departure is represented here. If we have complex poles in the given problem means, then we have to calculate the angle of departure also. The angle of departure is represented in a gray color. Angle of arrival representation is given below. In the given problem, if we have complex zeros, then we have to calculate the angle of arrival also. The angle of arrival is calculated from the complex zeros. This is indicated in this graph. Let us discuss about the point of intersection of the root locus on the imaginary axis. The points of intersection of root locus branches with the imaginary axis can be determined by use of Prout criterion. Alternatively, they can be evaluated by letting s is equal to j omega in the characteristic equation and equating the real part and the imaginary part to 0 to solve for omega and k. The values of omega are the intersection points on imaginary axis and k is the value of gain at the intersection points. Let us see the importance of the root locus. The root locus technique is an important tool in designing control systems with desired performance characteristics. The desired performance of the system can be achieved by adjusting the location of its closed loop poles in the S-plane by varying one or more system parameters. The root locus can be plotted in the S-plane by varying a system parameter, usually gain k, over the complete range of values. The roots corresponding to a particular value of the system parameter can then be located on the locus, or the value of the parameter for a desired root location can be determined from the root locus. Let us see the uses of root locus. The root locus technique is also used for stability analysis. Using root locus, the range of values of k for a stable system can be determined. It is also easier to study the relative stability of the system from the knowledge of the location of the closed loop poles.